Hi everyone, welcome back.
Welcome back. So today's topic, PLC architecture.
Sounds
The
good.
the organization of PLCs at a broad level, how the major components, how they are organized from a ecosystem perspective, and what you're likely to encounter, kind of like out in the real world,
Yep.
interacting with one. So, with that being said, we will enable our
Slide deck
clicker.
here.
There we
Yeah,
go.
there we go.
Um, so at the top level, PLCs. You guys saw them last quarter. Um, we may or may not have gone into a great deal of detail about them.
They
So
definitely learned about the scan cycle.
definitely learned about the scan cycle, and you guys kind of saw what inputs and outputs are on a PLC, but you saw a PLC that contained everything kind of in one module. So we're going to talk about kind of what what other PLCs and how they're typically employed
Yeah.
ends up looking like.
The bigger picture.
The bigger picture of what they are and those types of things. So you may have seen a diagram similar to this, but at the top level, a PLC is kind of broken out into kind of four kind of distinct areas. We have our kind of input side, and we have our output side, and then in between that we have a bunch of stuff that is internal to the PLC. That is our logic and our state tracking for inputs and outputs, essentially. Yeah,
Yeah. So before it's I think the important thing to realize here is you've got this input module and an output module, and before it does, like before that input module, the light going on actually affects the program, there's a file that gets updated. And that
yeah,
is that input file. And the same is true on the output side. Before it switches an output, that output file
get
gets
update.
updated.
Yeah,
And so the flow of things are the scan cycle basically is updating the input file,
comparing that to
comparing
the
to that the
logic,
program of the logic, all of it, like
all
the
of it.
entire program of logic, and then
Up,
updating the output
output
file.
file, and then finally the module updates the actual physical output,
Yeah.
right? Or represents the updated output, I should say. Um, and from this perspective here, or this aspect of PLCs, um, is really important to keep in mind, because the key thing that you should take away from this is that the input signals and the output signals are wholly separate from the logic that is actually being run, and the evaluation of the logic happens all at once every scan cycle. It does not happen on a input by input basis or output by output basis.
Or line by
The
line of
line, yeah,
code execution either.
No, it's like all of the logic gets evaluated, and so like the inputs are read. Those values are then updated to the corresponding logical instructions in the program. So if you have a normally open contact or normally closed contact, those update accordingly for the entirety of the program. And then the output file is updated according to the result of each rung, if we're talking about ladder logic. And then that output file is used to write out the corresponding actual outputs on the module.
Which is an important thing. You know, one of the most common mistakes with PLC programming for anybody who's done any sort of C-based or Python-based coding is that you think about executing line by line. If you have a line of logic that turns on
Yep.
an output, and then later on you have a line of logic that turns off that same output, it's likely never going to turn on,
Yeah.
because it waits until it evaluates the last line of logic on that program and then updates the output.
Yeah. And so, and here, what Jason is pointing out, we will definitely talk on in like more detail about how we deal with this peculiarity or this nuance about PLC programming, and you will definitely run into it. this quarter when you are programming.
Oh, yeah.
Like, this is a very common hurdle that everybody kind of runs into their first their first times like programming PLCs, especially when like the logic becomes a little bit more complex than just dealing with a button or a timer or something like that. If we take this a little bit further and we look at this from like a little bit more detailed perspective, a couple things about the input and output modules that are important to understand is that the input modules and the output modules, their outputs are grouped together in kind of like clusters of parallel connections, very typically. Unless we're dealing with a specialized module, we'll talk about those later on throughout the quarter, but we'll also talk about different modules here at a high level. On the left-hand side of the diagram here, we have like all of these input devices, and these are different switches. They could be sensors. They could be anything that's going to generate an input signal.
Yeah. So we see on there, we see a push button, a couple of push buttons. We see a level sensor and a limit switch.
All of these essentially are responsible for opening or closing a circuit, depending on like machine behavior or operator interaction. And at the end of the day, the input module is essentially a voltage detector. It's looking for a signal at these pins.
If we're talking discrete.
If we're talking discrete I/O, it is essentially behaving as a simplified voltage detector. And it's going to respond to a specific range of a voltage signal. So if we're dealing with 24 volts, which is really common in industry, I think pretty much every PLC module that I'm aware of utilizes as an input is a 24 volt if it's discrete.
Yeah. But there's a threshold that's less than that.
There's a threshold that's less than that.
And that's going to vary by manufacturer.
Yeah. And that's a specification that you will need to understand depending on the machine the PLC and the machine that you're interacting with. That's that'll come into your troubleshooting of its I/O and those types of things. On the output side here, again, if we're talking about discrete outputs, these outputs also tend to be clustered into groups of parallel connections where we're setting up a specific voltage relationship. But here, the output module is sending a signal or turning power on conditionally based on logic. And when we're looking at these modules and these clusters of parallel connections, they may or may not be required to be wired in a specific way. That's when we're talking about syncing and sourcing types of components. We will get into the details of that. That's kind of a little bit outside the bounds of the conversation for this discussion. But the thing to understand here, though, is that when we're wiring components to PLCs, it is going to be very common that there is some type of external power supply that is responsible for providing the voltage signals to the PLC. In previous circumstances or in the previous class, I think you guys had that experience where there was a separate power supply that drove the inputs and outputs for the PLC.
And this is an important thing to kind of like expect. The output pins and the input pins, those don't provide their own power. You have to externally provide that. And there's a very good reason for that. With one PLC, are likely going to want to control multiple different voltages. And your current is not necessarily driven by you don't want it to be driven by the PLC itself. You want to be able to expand the amount of current consumption your system is using as you add on different devices into that. And so by making the power supply external to the PLC, it makes it much more useful for a broad array of applications.
And this comes into kind of like one of the first broad categories of modules that you will likely, or types of input and output modules you will likely see, and that is, are they relay outputs or are they standard signal outputs from a module? A relay output module is typically capable of switching 120 or 240 volt power directly, whereas a regular digital or signal output module will only output a discrete 24-volt signal with a very small amount of current being capable of being driven by that output. But we'll talk about that in more detail as we go through things. So again, keep this in mind that there's an external power supply to either side of the PLC when we're dealing with these input and output modules. And it is also something...
And that's what you see there on the common power bus on the, to
Right.
the right there.
So on the common power bus to the right, that's a common power bus for the inputs, and then there's a common power bus for the outputs accordingly. I think the only other thing here that I think is probably worth pointing out at a high level is that there is some type of voltage protection from the PLC controller itself and the input and output modules. And so that might be optical isolation. I think that's the common solution today.
It's optical, yeah.
But there are older modules might use different methods for doing voltage protection.
Yeah.
And that's to protect the PLC from overcurrent and overvoltage events that could happen in the industrial environment. Yeah. So that the PLC doesn't die, only the module dies at a worst case scenario. That brings us to kind of like how we think about organizing these modules when it comes to the PLC itself. And there is a standardized way that these modules, or a common convention that is used for figuring out what I/O goes with what particular module inside of a PLC program. And understanding this is going to be very important for actually building kind of like the most important thing in any PLC program, which is going to be your tag table, right? So do you want to run us through the addressing here?
Yeah, so you see here on this, you've got your main CPU unit there, and next to that it has M0.0 to X.X.
Right.
And that's because those are just internal bits. They're memory bits.
Yeah.
And there's different flavors of memory bits. And that depends on what data type they are.
Yeah.
But those are going to be only internal. They don't actually switch anything external. They don't involve external pins.
No.
They're just internal, and so these are things that you use as part of logic commands. So these are things that you create on an as-needed basis. You have to be aware with those M1s is that they are all a shared registry. And so when you use one that like has a different modifier, so there's like MD is for integers.
Yep.
MW is for floating points.
Yes.
When you use MW1, it is the same as M0.1. And when you start using larger pieces of data, because MD is an integer and that's going to contain so many spaces of information.
So like a binary value is 1 bit, so it's 0 or 1, right?
Yeah.
An integer value can be it can be very large numbers, so you need multiple bits or a range of memory addresses.
Yeah, so these addresses will often, you can use the software to kind of help drive you when you're creating these, if you're creating these in a thoughtful way for your tag table.
Yep.
That's a big thing, because if you create them in order, then they will auto-generate the next block of resources that is needed.
Yeah.
So you don't need to worry about the conflicting addresses, but you'll get all kinds of red flags if you start creating ones that are over the top of another.
Right, and this is, and thankfully, in the past, we would have had to have done a lot of manual addressing of memory in this way.
Yeah.
Today, there's a lot of tools to help us manage this in a more effective and optimized
And it all
way.
boils down to being thoughtful when you create your your tag table.
Yeah.
When you're dealing with M addresses in particular,
Yeah.
You have to be concerned with that. So kind of think about blocking off areas for things that you know are going to exist in your program. Now the I or Q ones, these are auto-populated based upon physical pins.
Yeah. These I or Q addresses, so I is for input, Q is for output.
Yeah.
We'll talk about why it's Q later. Don't
Yeah,
worry about that
okay.
for right now.
But essentially, it just works from the nearest module is 0.0, the fourth module is 4.0.
And the dot zero at this point, so anything that's after the first number, so 0.0 and like 0.1, 0.2, 0.3, etc. Those correspond to specific pins on the input
Yeah, the
module.
actual terminals on there, like you've got 0.0 is the first terminal on that module.
Right.
And then the next module over, the first terminal is going to be
1.0.
1.0.
And then the next module over from there will be 2.0, and then 3.0, etc., and on and on. And this holds true for inputs or output pins. And so they do get a different prefix so we can tell them apart. So I for input, Q for output. But the addressing scheme otherwise stays exactly the same, regardless of how many modules are placed on the PLC. They start at 0 and they ascend in their address value. One quick note: it is you can't just continue to add I/O ad infinitum to a PLC with modules this way. There is an upper limit to how many modules a PLC will be specified or rated to handle.
Yeah.
That's something that you also need to be aware of when you're specifying or working with a PLC.
Yeah.
This is an example of what some Siemens modules look like, and with your time in the program, you will definitely run into modules that look like this. And these essentially connect to the side, so that you butt them up against one side of the PLC, and you just essentially daisy chain them out.
Yeah. If you look on the side of the one to the right here, you will see that there is there's a little door on the side of that there.
Let's see if I can point that out.
If you can,
So if you can
scroll
see
over that, yeah.
right over here.
That door there contains a little socket that you're able to plug into with the next module over.
And the way this socket interacts is that there's a lever right here where my cursor is, and there's one on this one here too, is that you open that door and you actuate that lever, and that extends out a connection.
Yeah, so that's like the male end of it, and then the female end is behind that door.
Yeah, exactly.
So that you can stack them together and create.
And so it's a convenient way to just connect these together. And in the background, essentially what's happening is that when you make these connections, the PLC is forming a kind of like simplified network of these I/O modules on the back end, so that it can pull individual pieces of or individual states of the I/O from all of the modules, kind of in a controlled way.
In a controlled way, and it's automatically addressing those.
And it automatically addresses.
So like the I's and the Q's, again, you don't need to worry about how they're addressed. You just need to worry about what terminal you're hooking things up to.
Exactly. And so you need to make sure that and it's very common for a module like this to have inputs and outputs. And you just need to make sure that you identify which ones are your inputs and which ones are your outputs and what devices is going where. So, and then at the, this would be an example of a PLC that is similar to the PLCs that you guys will be working with. Very likely, this is a Siemens S7 1200 with 2 modules and a power supply. Some PLCs can take a power supply or power directly from the wall, essentially 120 volts input, and be powered that way. Other versions or other models of PLC might require a 24 volt DC input to power up. In this particular case, that's what's required of this PLC. And with this particular power supply, this is actually connecting to the PLC in essentially the same way that the I/O modules are connecting to this PLC. There is a jack that you can basically you can butt these two things together and create a direct connection between them. There are also other power outputs on that power supply, so you could wire this to another PLC, for example, if that was a requirement, or you could use it to drive other things. Typically, you would not do that. The best practice would be to inputs get their own power supply, outputs get their own power supply, and then your PLC also gets its own power supply. So, and that's for signal integrity reasons.
Yeah.
Is there anything else that we want to?
I'd like to point out that the 1200 that you see there, it can be powered by a plug-in power supply by the side, but it also has two terminals at the top that allow you to plug in AC directly to it. This is different than a lot of other manufacturers.
Yeah.
Most of them don't allow you to just plug in 120 straight into the PLC.
This is a somewhat unique feature to the Siemens ecosystem, is that they allow you to do this.
But they don't allow you to do it on the HMIs.
That's really important.
That's really important if you don't want to blow up an HMI.
Yeah. All of the HMIs, and we're not really discussing them in the context of this conversation here.
Right.
But they are a separate device that a PLC will talk to over an industrial network. Those only accept 24 volt DC input.
Yeah.
They do not accept line voltage or wall power voltage.
But anywhere, wherever you are, make sure that you're hooking up the right power to it.
Yes, and it's just like that's one of the first kind of things that we're going to look at when we were wiring our PLC is like what are the fundamental power inputs that are required to get the PLC to work. Yeah. And that's going to be referenced in the documentation. That's not, and you can't anticipate that being the same for every model of PLC. So it's something that you actively need to seek out.
Yeah, and some devices, like they'll make the enclosure for it. They'll make the enclosure for it for multiple different models, and so there'll be labels on it, but that doesn't mean that you hook up those labels. In the United States, the way that those labels are in Europe, for instance,
or Asia, or these are things that you really like. This is where the details and some of the fundamental knowledge about PLCs comes from, is like there are these differences, and the context of like how you power one of these devices changes depending on kind of like where you are in the world.
Yeah. Like if you have one that says L1, L2, and then the L2 has a neutral underneath it, you need to be aware like that's going to be different.
Yeah, and you need to understand you need to go and look into the documentation and understand what they mean by that.
Because the manual is going to be for multiple different model numbers. You need to check what it means for your model number.
Exactly. And so, again, that's something that we got to watch out for. And that also holds true for how the inputs and outputs are set up on any one of these modules as well.
Yeah.
You can see that the modules have a standardized form factor. For the most part in the S7-1200 ecosystem. There are some modules that have a little bit more that are wider, but they basically conform to this inputs at the top, outputs at the bottom, but how those inputs and outputs behave changes model to model, and you need to look up the specifications for those modules to really understand that. It's very important. You cannot assume that every model is going to be wired and powered the exact same way. Just
otherwise, those actual model numbers there would be a lot shorter.
Yeah, they would be a lot shorter. So the model number. So like, this is actually something we should point out real quick since it's up here, and then we'll wrap this conversation. But we have a model number here, but then we have this more involved number down here. This code describes the exact model. This up here, this is the family.
That's the series of it.
Yeah, that's the series of this particular input device. And it can come so that you can have a series of these that have different features on them, different quantities of I/O, different voltages that they signal at potentially. some of them could have like high speed inputs and outputs on them.
Yeah. And one way to think about it is that that's kind of like the SM1223. That is kind of the family. So that's like maybe you've got a Toyota Yaris,
Yeah.
and then that other number is what depicts exactly what options you got on it.
Exactly.
Like if you actually managed to score
That's really
power
good.
windows on a Yaris.
That's a really good analogy.
Like that's what it is.
Yeah. And so that's something that we want to pay attention to when we're both looking at the modules that you guys are going to be using throughout your time in the program, but also it's something that when you go out into the field, you need to be aware of those differences. And different companies handle this differently. So this is also something that you need to familiarize yourself with on a kind of brand by brand basis, how this works.
Yeah, you'll be able to interact with whatever PLC you have to interact with.
Yeah.
It's just that you will need to ascertain the physical differences and the quirks
Yeah.
between them.
And so what we're laying down in the industrial programming class, MEC 153, is really about kind of like the generalized things that are going to be common across like all PLCs.
Yeah.
So I think that's a good spot. We will see you guys
In the next video.
in the next video.
All right. Have a good one.
Take it easy.